Hello and welcome back to another Medium problem. We're looking at 162, find peak element. So let's see. So a peak element is an element that is strictly greater than its neighbors, and given a zero-indexed integer array nums, find the peak element and return its index. If the array contains multiple peaks, return the peak to any of the peaks. Nice. You may imagine that nums at -1 and nums at n, so just outside of our array, have a height or value of -infinity. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. Okay, cool. So you could have a peak on, well, on the left edge or on the right edge if the successor of that edge element or the predecessor is smaller than that one on the edge. You must write an algorithm that runs in O n log n time. So we see that the values are integers. Well, are they integers? Integers, yes. They are integers. They have a range. We probably don't care so much about what that range is. And we know that two consecutive array elements always have different values. Right. So that's good. So we don't run any into like plateaus where we have 2, 2, 2, 2, 2, right? Or something like that. Okay, example input. So here we have an array of, I would call these heights, right? Height 1, 2, 3, 1. So this one is definitely the peak. The 3 is the peak because the left and right element are smaller. This one is not a peak because this one is higher. That one's not a peak because that one's higher. And the 2 is also not a peak because even though it's larger than 1, it's smaller than 3. And we return 2 as the index position, right? Return the index of the peak. Okay. The next example. So here we have another landscape. Let's see where the peak is. So if we iterate over this, we will find this is the peak at 6. So at element number 5, right? Yeah, that is the peak. All the elements are not peaks. Okay, cool. So now we have a linear time by just iterating through it and just looking if we have a peak left, or if we have a peak by checking the condition that the neighbors of the current element should be smaller than the element. So that would be, the naive solution would be O of n time and O of 1 space, because we just need to iterate and check. And once we find the index, we just return it. Well, I like to implement the easy solution anyways, just because we can. It gives us a little bit of extra practice. So let's just implement the one that we're not supposed to implement. Time and O of 1 space, and we'll do exactly what I just said we would do for I in range length nums. And then we say left value is nums at I minus 1. Well, actually it is float. It's infinity. If I equals 0, else it is actually the predecessor of I, and we have the right value, and that is also float infinity if I is equal to len nums minus 1. So when we're at the smallest element, at the last element, otherwise we are looking at the successor of the current element. And the current one, or mid element, is basically nums at position I. And then all we need to do is to check if left smaller mid, well, if mid larger than max left and right, then we just return I, because that's when we found a peak, right? Yes, so let's just run that as a test. Let's submit it. If it lets us allow us to submit this solution. Actually does. Okay, cool. So now let's try to improve this. Well, how on earth could we improve this? Well, one way to think of it is, well, we can exploit the fact that we should find any of the peaks, right? And it's guaranteed that the array contains multiple peaks. So if we should find one peak only, I think it would be difficult to find it, but we don't need to find a global optimum. We just can find a local one. So we just need to find a local peak. And we could just look at, you know, if we look at two numbers, we know instantly in which direction there is no peak. Right? If you look at 1 and 2, we know that into the left direction there is not going to be a peak. It means that the peak is going to be in the right direction. So we look at, so we should probably look at this part, this range of the array. So if we look at two consecutive elements, that tells us whether we should to the left or to the right of it for a peak. And if we use like a binary search approach, we could, you know, if we look at the, this is maybe the, wait, if those are the mid elements, you know, we would know, okay, we need to look in the right array for the peak and not in the left one. So if we use that idea, I think we're guaranteed to have the search space every time we make this decision. And while we do it, so for example here, if we look at those two elements, or let's say if we looked at those two elements, it points us into this array, this sub-array. And then next time we examine these two and it points into that, that's fine. Even though this would be a peak, there's also a peak here. So we don't really have to worry that the peak changes every time when we divide our array into two or by 2. So yeah, so let's use that approach. So that's going to be a log n time and O of 1 space solution. We'll start with the traditional binary search approach. So we have len nums -1. Not like this, like this. While left smaller equal than right. Okay, cool. So now we compute the midpoint. Left plus right divided by 2. And we're also going to look at the next value, so mid plus 1, to determine what its value is. So I'm going to write a little helper function here to deal with the fact when we try to get elements, well, the left neighbor of the first element, for example, get height, and then we say index. If index in 0 or len nums, return minus float infinity. Else we're going to return nums at position idx. Right, cool. So yes, so what we're going to do is we're going to take value 1 or height 1. Let's just call it h1, h2, and we're just going to get those height values, and then this one is mid plus 1. And now we're going to make a decision. If h1 is smaller than h2, that means we have to go into the right sub-array. So we're going to say that left equals mid plus 1. Otherwise, we're going to say that right equals mid minus 1. And the plus 1 minus 1 is important so that we don't run into an infinite loop. Yes. And what we also should do is we should probably check if we are at a peak. So we're going to actually check as well what is to the left of this. And if h1 is larger than the maximum of h0 and h2, we're going to return mid. That is our index. Yeah, and I think that is about it. And we actually don't have to do anything here because it's guaranteed that there are peaks. But what we have to do, no, actually this is fine. So one of those two cages will always catch. And we're guaranteed we're not going to see an equal anyways, so we don't have to worry about that. So let's see if that works. Okay, typo. I'm making a lot of typing mistakes recently. So I actually get an output of 0, which is of course not great. minus 0 is also nonsense. That needs to be minus 1. All right, so the test case is pass. Let's submit this now for the real test. And okay, so now we only have one element. Interesting. So if we only have one element, what happens? So what happens is that left is 0 and right is 1. While left is smaller or equal than right, then we're going to compute mid. Mid is going to be 0. So in theory, it should work, right? Output is null. I mean, we could just deal with this, as an extra edge case to handle, but I'm wondering why this logic is failing. So the length of nums is 1. So left and right are 0. So if 0 plus 0 is 2. And we insert this loop because we have an equal here. So mid is 0. Now we get h1, 0, h1, h2. So that should be minus infinity. This should actually be the height of 1. And this should be also minus infinity. Oh, so this is wrong. Minus 1. That's what the index needs to be here. And if we take this little example, nums equals 1. And if we run the test, it should return 0 because that's the 0th index. So that's correct. So I think that was the error here, that we were checking the wrong index. Yeah. And we're going to submit it. Okay, at last. Again, too many small errors. Luckily, we were able to fix them quick. But if you're in an interview and somebody doesn't make those errors, that person might be ahead of you. So again, note to self, pay more attention, be more patient, instead of trying to rush through this.